In this lecture, I will go through a example in which the CLTD CLF method will be used to calculate the cooling load for a building. We have gone through the equations that are used in the CLTD CLF method, which require a number of factors which are obtained from tables, and as we go through the solution of the problem, you will learn to use the tables. So that is important that you use the tables correctly. So that is the problem statement. You are given the size of the building, and it's an office building, and we are told that in this particular building only two of the surfaces are exterior, that is the roof and a wall that is facing the west direction. The statement that is given in this problem, that assume the thermal conditions in all other adjacent spaces are the same as those of the office space. That statement tells us that there is no heat gain from partitions, because any adjacent room or space is at the same temperature as that of the conditioned office space. We are asked to find out the cooling load at 1400 hours on July 21st, and there are a number of other pieces of information which are provided for that particular office building, that is its latitude, the types of windows, what is the size of the window in terms of the percentage of the wall area that they take up, whether they have shading. Yes, they have shading because they are using Venetian blinds. We are given the U values for the wall as well as for the roof, and there is also a mention of the wall type and roof type. We will come to those things when we refer to the tables. The inside and outside design conditions are given. The occupancy schedule is given. The equipment load is also given to us. We are given the requirement for ventilation, that is the office environment is non-smoking. The schedule for lighting is also provided to us, and the infiltration load is also given as 0.3 air changes per hour. If you recall, the loads can be divided into the two broad categories, that is the external loads or from exterior surfaces. Exterior surfaces are those which are directly exposed to the solar radiation, and the internal loads, in addition to that, you will have the ventilation load. So in the first case, we have the conductive heat gains through exposed wall, exposed roof, any door or window that is exposed, and if there is a window, because it's a transparent surface, the load or the heat gain through the window is further divided into two parts. One is the conductive heat gain, the other is the solar gain or the thermal radiation which is transmitted through that transparent surface. Okay, so we will start with the external loads and then proceed forward, and as we proceed you will see how we make use of the tables that are given to find out various factors and values. So we will start with the roof, which is an exterior surface, and we are told that it is of type 4 without suspended ceiling. The U value of the roof is given, and to calculate the heat gain we need to first find out the CLTD value from table 4-14, and once we have got that CLTD value, we will modify that to CLTD adjusted according to the conditions given in the problem. So the equation that we will be finally using will be Q dot is equal to UA CLTD adjusted, and before we are able to do that, we need the value of CLTD from table 4-14, and I will go to that table and you will see how we make use of that table to find out the CLTD value. So you can see that we have tables 4-1 to 4-15 which all relate to the cooling load calculations. In addition to that, when we find out the cooling load, we will also at some point need to find out values from the psychrometric chart. So now let's proceed to the appropriate table, that is table 4-14, which is for cooling load temperature difference for flat roofs. So we can see that the CLTD value for flat roofs has two sets of data, one for roofs without suspended ceiling, the second for roofs with suspended ceiling. We have a roof without suspended ceiling, so that is, we will use that set of data, the first one. And we are also given the roof type, so that is, roof type is roof number 4, so that has also been marked out. Now you have the time, and we need to find out the cooling load at 1400 hours. So you can see this is the column that you will read the value from, and once we have got the right roof type and the time, we can find the CLTD value. So if you look at the CLTD value, you can see it is 24 degree C or 24 Kelvin, because it's a temperature difference, it is the same, and that is the CLTD value. The next thing is to modify this value, that is, we need to find out CLTD adjusted, and the formula for CLT adjusted is given at the bottom of the table. You can see this formula over here that is given to us, in which you use the value that you have just obtained, that is CLTD is 24, then 25 minus TI. TI is the indoor design temperature, which is given to us as 24 degrees C, and the temperature TAV is the average outside dry bulb temperature, which is given to us as 29.5 degrees C. So we just insert those values and find out the value of CLTD adjusted, and then find out the heat gain through the roof, and that is what's done in the solution. So we go back to the solution and find out what's the resultant heat gain. The area of the roof, you can see, is the area which is 15 meters by 25 meters, so that's the area of the roof multiplied by the overall heat transfer coefficient, which is given in the problem, and CLTD adjusted is found out by ourselves, and we get the heat gain through the roof to be 4877 watts. The next part of the exterior heat gain is from the wall, and again the U value for the wall is given, and we are told that it is type F and it's a west facing wall. You will see that we need the orientation for the wall as well, and that is, it's a west facing wall. So in the figure you can see the 25 meter by 3 meter wall is the one that is facing the west direction, and in this wall we also have windows which take up 12% of the wall area. That means the net area for the wall through which the conductive heat gain will take place will be 88%. So we multiply the area of the wall, the gross area, that is 25 into 3 square meters, by 0.88, and that is the net wall area. So you can see that it has been worked out as 66 square meters. Once again we will need the value of CLTD for this type F wall, which is west facing at 1400 hours, and that is obtained from table 4-15. Once we have got that value, again we will find out CLTD adjusted and then calculate the heat gain for the wall. So I will move on to table 4-15 and just and verify that the value that we have shown over here, 11 degree C, is indeed the value that will be obtained from the table. So you can see that in the first column we have the wall type, then the orientation is also given, and the other thing that we need is the solar time. So the wall time type in the first set of data is for wall type G. We have wall type F, so we scroll down to the appropriate wall type, that is F over here, you can see, and that will be the set of data that we will be using. So we have wall type F. The orientation is that the wall is west facing, so that's the column that we will work with, and the time again is 1400 hours. And then we read the value of the CLTD under these conditions. The CLTD value is 11 degree C, and that is the value that we have used. Once again, you will use the same formula for finding out the value of CLTD adjusted, which comes out to be 12.5 degree C, and then we move to the heat gain, and I'll go directly to the solution to see the result of the calculation. So you can see that the heat gain through the wall is 1238 watts. Okay. The CLTD value is 11 degree C. The net area, remember, we have to use the net area. If there is any wall or door in the wall, we have to subtract that area, and then the net area of the wall will be used in this equation. We are also told that there are windows in the wall which take up 12% of the area of the wall. So we need to find out the load through the windows, the conductive heat gain, as well as the solar gain through the window. And again, we will need to find out certain values from the tables to work out those heat gains. Okay. So when we refer to those tables, the information that we have for windows is again the orientation, it's west facing. The construction of the window, it is double glazed with 6 mm airspace. When we say double glazed, it means there are 2 panes of glass with a 6 mm airspace between these panes. That construction will lead to reduced heat gain, conductive heat gain, because it has a higher thermal resistance, and it also reduces the noise levels inside the conditioned space. The type of glass sheet that is used is regular sheet glass, and inside we have shading provided by Venetian blinds, which are light Venetian blinds, and this information will be required to find out certain values from the tables, and that is what we will do as we proceed with the conductive and the solar gains through the windows. The area, of course, is 12% of the wall area. The wall area is 75 square meters. We multiplied by 0.12, and the area of the window comes out to be 9 square meters. You can see that the U value I've written as 3.5 watt per meter square, and it is taken from table 4-4. So it was not given to us. We had to refer to table 4-4 and then obtain this value. Once we have got the value of U, then the conductive heat gain is fairly straightforward. It is the equation for heat transfer, that is UA delta T, where delta T is T outside minus T inside, and that will give us the conductive heat gain. So so what we need to now do is to just see how we use table 4-4 to find out the U value. So I will move to table 4-4 and then return back to this solution to work out the heat gain due to solar gain or transmission of solar radiation through the window. Table 4-4 gives us the thermal resistance of unit areas of selected building materials, and we start by looking at this list of building materials and see where we have some information about glass. It's not over here, so we will scroll down. We have the insulating materials, interior materials, then we have the air resistance, and finally we have flat glass, and that is what we will refer to find out the U value. You can see that the U value for flat glass is given, and it is given for two different conditions. One is for summer, the other is for winter, because we need to find out the cooling load for summer, that is in July. So that is the column that we need to work with. Then you can see, because it's double glazed glass with a 6 mm air space, this is the right choice, and against these two values we will again find out the U value. And you can see that is 3.5 watts per meter square Kelvin. That is the value we had used in the solution. We will now return back to the solution to see how we will calculate the heat gain due to transmission of solar radiation through the window. The equation is given to us, which requires us to find out the value of the maximum solar heat gain factor, then the shading coefficient, and the cooling load factor. Area of the window, of course, we already have worked out. So these three values, that is maximum SHGF, the shading coefficient, and the cooling load factors, will be obtained from tables 4-10, 4-11 and 4-12 respectively. You can see that those values are 690, 0.51 and 0.53, and once again we will go to the tables and see how these values are obtained. So the first is the maximum value of solar heat gain factor. We are given two sets of data, one for 32° north latitude, the other for 40° north latitude. The building that we are interested in has a latitude of 40° north. So the second set of data is what we are going to use. The SHGF value is to be found out for the month of July, and that's all we need. And of course the orientation is that it is west facing, because the windows are in the west wall. And once we have got that information, we again find out the value of maximum SHGF, that is solar heat gain factor, which is 690 watts per meter square, and that is the value you will see we have used in the solution. The next is the shading coefficient, for which we move to table 4-11. Just scroll down, that is the next table, shading coefficient, and we are given various options regarding the shading coefficient. We know we have Venetian blinds inside. What type of Venetian blind? We have light Venetian blinds. Then what type of glass we have? We have double glass in terms of the construction, and the glass sheet is regular sheet glass, so that is chosen. So you could have double glass, but that glass sheet itself could be of three types according to this particular table. It could have been regular sheet glass, it could have been plate glass, or reflective glass. We now use this information to find out the value of the shading coefficient. And the value of the shading coefficient is 0.51. That was the value that we had used in the solution. And finally, we need the cooling load factor, for which table 4-12 is the one that we will use. Once again, the orientation, it's the west facing window. And the solar time is 1400 hours. Against which the CLF value will be read. Which comes out to be 0.53. So that is the information that we required to calculate the solar gain from windows, and we go back to the final result for that. You can see the three values, 690, 0.51 and 0.53. Then the final result will be that the total heat gain through the windows will be the sum of the conductive heat gain and the solar gain, which comes out to be 2026 watts. Another external load is the infiltration load, but the calculations for infiltration and ventilation are quite similar, so I have not found out the infiltration load at this point. I've left it at the, to be calculated at the end. The next thing that we will do will be is that we will calculate the internal loads, and then we will find out the load due to infiltration and ventilation. And remember, the internal loads could be due to three sources, that is occupancy or people. We can have internal load due to lighting and any appliances or equipment that are that cause either sensible or both sensible and latent loads. When we talk about the load due to occupancy, it will have two components, sensible load and latent load as well. What we will need is the heat gain per person according to the activity of the person in the conditioned space, and then of course we must also know how many people are inside the conditioned space. We are told that the occupancy is 40% and also that they are present in the conditioned space from 0800 to 1800 hours. That is a total of 10 hours in the conditioned space, and the office environment is non-smoking. That will also be information, that information will also be utilized at some point. What we will need is the sensible heat gain per person, then we multiply it by the total number of persons, and remember, because it's an internal load which is sensible, we also need a cooling load factor, and that cooling load factor you can see has been given as 0.8. Once we have got the sensible heat gain, we move on to the latent heat gain. Again, we need the value of the latent heat gain per person. We multiply it by the total number of occupants and then get the latent heat gain, and the total heat gain will be the sum of the sensible and latent heat gains. So you can see that again we need to refer to two tables, tables 4-7 and 4-9. One will give us the value of the sensible and latent heat gains, both are obtained from table 4-7, and the cooling load factor will be obtained from table 4-9. How do we find these values, that is what we need to look at next, and I will go to those tables. Table 4-7 is heat gain from occupants. So this is the heat gain per person, and the units are in watts. And you can see the first column tells us the type of activity. So we are told that the activity that we have is office work, and against that the heat gain is 150 watts. The third column tells us what percentage of this heat gain is sensible heat gain. So we are told that 55% of this value is sensible heat gain per person. So the sensible heat gain will be 150 into 0.55 watts, and similarly the latent heat gain will be the remaining fraction, that is 0.45 or 45%. So that will be 150 into 0.45 watts. So that is all we require to calculate the load that is sensible and latent. The next thing that we need is the cooling load factor, and that is obtained from table 4-9. So I will move on to that table as well and read the value of CLF, and then we can go back to the solution to work out the total heat load or the heat gain due to occupancy. We have to be a bit more careful in reading the values of cooling load factor from this table. Of course, the first horizontally you can see there are a number of columns for total hours in space, and we know that the people enter at 800 hours and they leave at 1800, so they stay in the conditioned space for 10 hours. So that means this is the column that we will need to use, and against that we also have the first column which is hours after each entry into space. And this is where you have to be careful how to interpret this statement. We are told to find out the cooling load at 1400 hours, and the people enter the conditioned space at 0800 hours. So what we want to see is that at the time that you need to calculate the cooling load, how much time the people have already spent in the conditioned space. So if they have entered at 8 and we are at 1400 hours, that means they have spent 6 hours in the conditioned space. So that is what we mean by hours after each entry into space. So you will use the column which has a value the value of 6. Okay, it would have been incorrect if I have used the value 14. So this is how much time has elapsed since the people entered the space until the time you are interested in finding the cooling load. So once we have correctly marked these two values, then we can easily read the value of the cooling load factor. And the cooling load factor comes out to be 0.8. We can go back to the solution and verify these values that we have obtained from the two tables. So you can see that the heat gain was 150 into 0.55, that is the sensible heat gain. The cooling load factor is 0.8, and similarly the latent heat gain was 150 into 0.45, and then the total load due to occupancy comes out to be 5340 watts. The cooling load due to lights, it's given by the formula that Q dot is equal to the wattage multiplied by the utilization factor multiplied by the ballast factor and the cooling load factor. The wattage is given as 17.5 kilowatts, so make sure you convert it into watts. I told you earlier that if the utilization factor is not given or information regarding the utilization factor is not given, then we take the default value to be 1. So because it was not provided to us, we have taken it to be 1. The ballast factor we are given in the problem statement, it is 1.2, so we have used this over here. And then the cooling load factor, you can see, is taken as 0.92, and again that will be obtained from a table, that is table 4-6. How do we read that value? That is next view what we are going to look at, and we will move on to table 4-6. The cooling load factors for lighting, you can see that we are given the cooling load factors for two different types of fixtures. One is fixture X, the other is fixture Y. And if we read the problem, you are told that the fixture type that we have in this problem is fixture Y. So that is the set of values we will select, and we know the hours of operation are 10 hours. And in the first column we have number of hours after lights are turned on, and this is value is again worked out similar to the value that we had used in the case of occupancy, that how much time has elapsed since the lights were switched on until the time you are finding out the cooling loads. So we start from 800 hours when the lights are switched on, and we are finding out the cooling load at 1400 hours, so 6 hours have passed until then. So that is again marked over here, against which we will read the value of the cooling load factor for lighting. Which comes out to be 0.92, and that was the value that we had used. So we will go back and find out the resultant cooling load. Which comes out to be 19,320 watts. The equipment load is sensible, and in this problem we are told that there is also a latent load. So the wattage is given for the equipment. You have to, because in the case of sensible load we need a cooling load factor, so wattage is given as 12.7 kilowatts. The cooling load factor for equipment is the same as that for lights, so you don't have to find out that cooling load factor again, just use that value that you had used for lights, 0.92, and you get the sensible load. The latent load will be used as it is, just convert it into watts, and the total load due to equipment comes out to be 13,484 watts. And at the end I will calculate the infiltration and ventilation loads, which I had as mentioned earlier, because the equations are the same for both, we have lumped them together at the end. So the infiltration load, we are given the number of air changes per hour, that is 0.3, so need to find out the infiltration rate in cubic meters per second first, and then you will have to convert it into liters per second. So the formula is quite straightforward, that the infiltration rate in cubic meters per second is number of air changes per hour into the volume of this conditioned space divided by 3600. The volume of the office building, you just multiply the three dimensions, 25 into 15 into 13 cubic meters, and we get the infiltration rate in cubic meters per second. You multiply it by 1000, and the resultant infiltration rate is 93.75 liters per second. Then we calculate the infiltration load. Again, that has two components, the sensible and the latent components. The formulas are given to you. You can see over here, that is the sensible load due to infiltration, and T naught minus Ti is the temperature difference between the outside and inside design conditions. That gives us a value of 1268 watts. Then we calculate the latent component of the infiltration load, and in that formula we need the humidity ratios at the outside and inside design conditions, because we are given the dry bulb temperatures and the wet bulb temperatures both outside and inside. We can use the psychrometric chart. That is what I had referred to earlier, that at some point we will need the psychrometric chart. we find out the values of the humidity ratios under the two conditions, substitute those values over here, and we get the latent load. So the total load due to infiltration is 2815 watts. Then we lastly come to the load due to ventilation, and that load is not given to us directly, but we are given some information which will be utilized to read the value for ventilation from table 4-1, and that information that we require is that we have an office space with a non-smoking environment, and if you read the statement over here, I've already written what value I've taken from table 4-1, that is 2.5 liters per second per person. And again, how this value of 2.5 liters per second is obtained, once we go to that table, it will be quite easy to see how we have found that value. So this is table 4-1. So the table number is missing over here. I'll just enter it. You can see we have the outdoor air requirements per person in liters per second. We have just 3 options over here, that is offices, meeting and waiting spaces, and lobbies. So obviously we have an office space, and inside the office space we again have 2 options, whether it's a smoking environment or non-smoking environment, because we are told that the environment is non-smoking type. So we have an outdoor air requirement for ventilation of 2.5 liters per second per person. So again, to find out the total ventilation requirement, we have to multiply this value by the total number of people in the conditioned space, that is 40. So we can return back to the solution, and you can see that the value 2.5 is multiplied by 40, and the values for T0 and Ti and W0 minus and Wi are the same as we used earlier for the case of infiltration. You will find out the sensible and latent loads due to ventilation, and the total load due to ventilation will be the sum of these, that is 3003 watts. And finally, we will sum up all the loads to get the space load and the ventilation load. Added together, these two will give us the load on the cooling equipment. So that is the total load on the cooling equipment, the space load, and the ventilation load, and that comes out to be around 14.82 tons of refrigeration. So I will suggest to you to become familiar with the use of these tables, because that is the key part of the solution. The equations are quite straightforward, and what you can do yourself is just solve the same problem with some changes. For example, you can change the orientation, you can use east facing wall, you can find out the cooling load at any other time, maybe at 1600 hours. So you can change make a few changes yourself, and that will help you become familiar with the use of these tables. And that is all regarding the cooling load estimation, and we will move on to a new topic in the next lecture.